Hello everyone, this is Mustafa Qadoura. Today we will talk about quantum computing and we'll discuss the differences between classical bit and quantum bit. Let's start by understanding a classical bit. Consider you have a coin and you are tossing it. You have two possible outcomes. It can be heads or tails. If you added a second coin, you have four possibilities. The first one can be heads and the second can be heads, or you can have heads tails, tails heads, or tails tails. If you added a third coin, you will end up having 8 possibilities, which are listed on the screen. We conclude that with n coins, there are 2 power n possible outcomes. Now consider a dice and you are rolling it and looking for the number that you are getting. If you are rolling a single die, you have 6 possibilities, which are 1, 2, 3, 4, 5, 6. If you added a second die, you will have 6 by 6 possibilities, which are listed on the screen. For example, the first die can show you number 1, the second one can show you number 1. Or the first one shows you number 1, the second shows number 2, or 1, 3, 1, 4, etc. And if you added a third die, you will have 6 power 3 possible outcomes. So we can conclude that n dice gives you 6 power n possibilities. Now let's try to understand how much information a coin and a dice can carry. Consider that I have the 7 colors of the rainbow and I want to communicate them or encode them using 3 coins or 2 dice. For example, to represent the color yellow, I will assume that I am tossing 3 coins and I'm getting heads, tails, heads in this order. Or I will assume that I am rolling 2 dice and I'm getting the first die giving you number 1 and the second die giving me the number 3. So we can see that it takes me 3 coins to represent 7 colors. However, it takes me only 2 dice to represent that. So as a conclusion, a coin carries less information than a dice. That's because a coin can distinguish 2 states, however, a dice can distinguish 6 states. So we say that something with 2 states carry the smallest amount of information. In classical computing, we use binary digits, which can take 2 states, either 0 or 1, and we call it a bit. Stands for binary digit. Let's now look at the quantum bit, which we call it qubit. A qubit is similar and different to classical bit. Like classical bit, it can be either 0 or 1. However, in classical bit, 0 and 1 are the only 2 possible states, while for a qubit, it can be a combination of zeros and ones, which we call it superposition of 0 and 1. We can visualize the quantum 0 and quantum 1 states as the north and south poles of a sphere of radius 1, which we call it Bloch sphere. A qubit can be any point on the Bloch sphere. For example, consider a point that sits on the equator, which is halfway between 0 and 1. It has this mathematical representation of the superposition of 0 and 1. We have other unique states on Bloch sphere, which are the intersection of the x-axis, y-axis, and the z-axis with the Bloch sphere. These are all possible states that a qubit can handle as a superposition. We just concluded that a die can carry more information than a coin, because a die can distinguishes 6 states. However, a coin can distinguish only 2 states. So the dice is more powerful than a coin. On the other hand, a qubit can be any point on the Bloch sphere. We have infinite number of superpositions between 0 and 1. So the quantum bit encodes a superposition of 0 and 1, allowing the quantum computer to process multiple possibilities at the same time, making a quantum computer much more powerful. This concludes our video. See you in the next one.